scholar in NIST Gettysburg, Maryland, US in 2002. And also he worked for Johns Hopkins University in 1993. And also IBM Zurich Research Center in 1990. He is a recipient of very prestigious awards, including TÜBİTAK Research Encouragement Award, Mustafa Parlar Research Encouragement Award, and also Young Science Award from Turkish Academy of Sciences. And today he's going to tell us about generalized measurements and computation.
Thank you very much. I thank you for nice introduction, but also for this nice organization and invitation. You know, it took longer for quantum than electromagnetism to find applications. After a century, now we are at an age of having quantum technologies, and we have already heard a lot of talks pointing in this direction. I hope that we will have some more. Well, this is what I call the Mona Lisa of quantum mechanics. Wherever you go, they look at you, not for this, but after this meeting, physicists agreed more or less, in spite of some objections, interpretation of the wave function. This is not a wave function, but the probability density as a function of position. You have a state, initial state. When you do a measurement, you collapse it. Collapse actually here, it means you make a narrower wave function if you want. So you think that you determined the position. And the rule is the Born rule. The projection or modulus square is proportional to probability. If it can be normalized, it gives the probability. And if you look at this product, it is an analog of the cosine squared of the angle in real space. Well, if you look at a general variable, some dynamical variable, you can talk about expectation value, which is the mean value. It can be easily calculated by trace of this product of so-called density matrix and your quantity. Density matrix carries whole physics. It has just three properties. It is a square matrix, a Hermitian one, trace one, and all eigenvalues positive. This last one is very important in some problems. This is the basic thing that it decides. So the number of free parameters for a density matrix you can easily calculate is d squared, because you have d diagonals, and for the off diagonals Hermicity reduces it to half, and you have d squared independent parameters. Because of normalization or trace one condition, you have d squared minus 1. So in 2 dimensions, you have 3 parameters. In 6 dimensions, you have 35 parameters. Density matrix is a way of doing this. You write a square matrix, Hermitian matrix, with positive eigenvalues. This is one way. This is what I would call as a standard formulation of quantum mechanics. But there is another approach. This proposal, he didn't call it in this way, was due to Schwinger. If you think of P and X, just the conjugate variables, what happens, or what is the analog of this in finite dimensions? Not in infinite dimension, but say in 2, 3, 4 dimensions. I do this, I never know anything about the others, say 5 or 4 possibilities. Probabilities are 1/5 all the way. This interesting idea has today many important applications in quantum information theory, in tomography, cryptography, and also discrete Wigner function. This is what we call mutually unbiased bases. Think of 2 bases in Hilbert space, A and B. The condition is that projectional any member of the first bases is same for all the members of the other bases. So normalization requires this is 1/d. For d equals 2, simplest case, these are nothing but, for instance, z and x eigenstates. Spin projection along z direction, spin projection along x direction, as an example. Well, mutual unbiased bases are important because if you do measurement using mutual unbiased bases, you obtain information about the density matrix in the optimal and the fastest way. It's important for tomography or any kind of measurement. Well, so number of mutual unbiased bases, by the way, let me go back. If you divide the number of unknowns, and each time you obtain, because of normalization, not d, but d minus 1 parameters, must be d plus 1 to have the whole information. Then you might say that there should be a detailed balance in the universe. We say this in something similar in Turkish, so that we should be able to find all the parameters. But if you calculate this, d plus 1, for 2, it is 3. So z, x, y projections, usual things. This is nothing but the Bloch sphere representation, for instance. But if you go to some higher dimensions, for instance, for dimension 6, you would expect 7 such bases. But till today, no one has been able to find these 7 bases. In spite of huge supercomputer calculations, no one has found. We only have, for the time being, 3 mutual unbiased bases in dimension 3. And there's a strong evidence, not a proof, for absence of the 4th one. So this is d equals 2, as I said. And known solutions, when d is a prime number, or when d is a power of a prime number, there is a recipe. There are ways to find the mutual unbiased bases. One thing about mutual unbiased bases is it allows us to define some analogs of uncertainty principle. Uncertainty principle, in simple case, is just something like this. We relate the variances or spread of the measurements of 2 variables, A and B, if they don't commute. But we can generalize this idea. Because the idea is, if you know A exactly, you don't know anything about B. If you know B exactly, you don't know anything about A. If you have more than 2, instead of P and X, say 2, 3, 4, 5 mutual unbiased bases, you can generalize this idea. But in this case, instead of writing variances, why not to use entropy? For instance, Shannon entropy, or whatever you want. So you calculate Shannon entropy for A, for B, for C, different variables. You can generalize uncertainty principle. This time we call this as certainty because we have a upper bound. For up to d plus 1 measurements, you can do this. This is a very recent work which will hopefully appear soon in archive by a member of our group, Bilal Cantürk, sitting at the back. Well, the usual time evolution that we are familiar from standard quantum mechanics is the unitary one. But we can think of more general evolutions if you consider mixed states, or maybe you can think of so-called quantum operations. These are the most general operations that we assume in quantum mechanics, where you not only start with your state, but perhaps something else. Let's call this as environment, and they undergo, again, a unitary transformation, and the environment is measured. In fact, this measurement is not in fact necessary. Whether someone did the measurement or not is not important. You simply do a trace operation. You don't worry about things happening in the environment. You just look at your own wave function, density matrix. If you do so, this is what we think the most general evolution, as I said. Among them, you might think that which environment should I use? What must be the size of the environment so that at the end I can define my density matrix exactly with d squared minus 1 parameters. This is what we call symmetric, informationally complete, positive operator valued measures. In this case, instead of your projective measurement, final D orthogonal states, you don't consider, if you calculate this, you should consider D squared equiangular vectors. And normalization requires that these projections should be 1 over D plus 1. There is a conjecture by Gerhard Zoner, coined in 1999, the last year of the millennium, in his PhD thesis, but it was rediscovered 5 years later. It was written in German. Zoner's conjecture, a version, says that there are always, in any dimension, D squared equiangular vectors. There is no proof, but a member of our group, Solomon, thinks he has something to be published maybe a few more weeks later. Well, I talked about mutually unbiased bases, and the SIC-POVMs are taught, it's a special case for generalized quantum measurements, are two equivalent ways of doing tomography or describing a quantum system. Here we have D plus 1 bases. Each basis have D parameters or D minus 1 free parameters. Here we have no bases. We use environment to project our system on D squared equiangular vectors. Well, to compare them, in conventional measurement, you do a measurement, you know that with probability 1, your value is, say, something, and 0 probability for the others. This is standard for Neumann-type projective measurement. But here we have, in the first case, yes, we have a yes for one of them, but no for the others. But for the other bases, we have just maybe. Maybe means 1 over D probability. Here in this case, we have a value yes, but we can't say no for the others because all vectors have some projections on all. But in practice, these two types of measurements are very, very important in applications, and they are related. This relation is taught to be, there have been some claims through so-called finite affine place. The idea started with Fano. Fano taught years and years ago generalization of standard geometry. Standard geometry involves uncountably many points. What happens if we have finite number of points and if we define, axioms, parallel lines, points on lines, things like that? For instance, this is an example with 4-point space, and this is a so-called order 3 affine plane with 9 points. In general, if you have order D affine plane or finite affine plane, you have D squared points. And the idea is, of these points, this 3 denotes the dimension of Hilbert space. These points, 9 points, correspond to SIC-POVMs, equiangular lines. And these lines, you see, these are parallel lines. They resemble parallels that you learned in elementary school, but these lines are also parallel. The number of these triples, parallel lines, is 4. They correspond to mutual unbiased bases. There is no direct proof for that. The problem, you will see, is this is an example for 4 bases, and this is 4. This I borrowed from Wikipedia. You can obtain this yourself. As you see, for instance, look at this color, for instance, this one. This line is assumed to be parallel to this line. There are ways. If you define a finite field using this arithmetic, you can obtain these curves very easily. Well, this is the summary of what I said: SIC-POVMs and mutually unbiased bases. And when I was dealing with this problem, I saw a work by Michel Plana, and we communicated. And in fact, without seeing each other, we wrote something about, this is part of the figure, construction of SIC-POVMs using these permutation groups. And this is actually an application of idea of Zoner. Here you have a so-called fiducial vector. You have a seed. Then you apply some operators, x and z, in this way, powers of x and power of z. A version of Zonner's conjecture is that there is always a fiducial vector in d-dimensional Hilbert space so that you can obtain SIC-POVMs in this way. The POVMs we obtained were information complete, but unfortunately not symmetric. So this is not easy. And this has been published through Michel Pellerin. I came to know about this journal, so-called Open Science. So no payment for anything. Anyway, well, let me finish this story, connection between mutually unbiased bases and SIC-POVMs. There is a claim, there is no proof yet. Zonner conjecture is today 20 years old or more, but many people believe that there are equiangular lines in any dimension. There is a recipe for mutually unbiased bases for powers of primes. Very, very interestingly, it is known, there is a mathematical proof, finite affine planes exist also for powers of primes. But there is no proof for absence of SIC-POVMs for mutually unbiased bases, and most important thing is for dimension 6, this is the first non-trivial basis. It is not a power of prime. This is still an open question. 6 is a very small dimension at first glance, but it is actually not. Well, now I will run and connect this to, in almost 10 minutes, to quantum computation. This means that that will be very fast. This is our qubit. You know, a qubit is the simplest quantum object you can think of, but it is classical in some sense because you can introduce a hidden variable model for a qubit. Because this is an example. But when you have two variables that can be measured together, that's two commuting observables, there is a problem. For instance, B measured with A or B measured with C, but A and C cannot be measured together. The question is B the same when it is measured with A or with C? The answer is, in general, no. This is what we call contextuality in quantum mechanics. There are many examples, but I should mention one of the least known examples, which is actually the most important one. The problem is you have 5 variables that takes values plus and minus 1, and the question is if you form this A, B, B, C, C, D, D, E, E, A sum, what is the minimum value for this? You can easily check that this can never be less than minus 3 classically. In the sense that if your system is not contextual, it means that this A here, A with E, and this A here, A with B, must be the same A. But in quantum, this is not the case. This value in quantum mechanics turns out to be as small as 5 minus 4 times square root 5. And this has been observed experimentally in many cases. It is now more than 10 years, right? Our colleagues' work. And simplest cases, if you take a spin 1 system and define your A operators in this way, A1, A2, A2, A3, etc., commute, if you take these spin projections in orthogonal directions. There's a question, there's a problem. To our surprise, we realized that no one has found states that violate this inequality or states that never violates. This is a complicated problem. This is an example for torus. Torus is 1 sphere times 1 sphere, that is circle times circle. But in KCBA's case, it is at least sphere times sphere. It is even more complicated, but we have, or our group member Frat has some calculations for this case, for general case. Well, these two, this and standard Bell theorems are actually manifestations of results of more general Cohen-Specker theorem. Bell, and by the way, this is famous Bertelsmann. He is famous because you know him from his socks. In his manuscript, Bell mentions Bertelsmann's socks. This picture was taken in CERN when he was visiting. Well, let me remind you and just jump to algorithms. This is the standard CH SH form of the inequality, and this is also violated very easily. This is all in textbook standard calculation, and we generally say that this is a manifestation of non-locality of quantum mechanics. Let me just make a comment at this point. Yes, Bell-type inequalities show non-locality of quantum mechanics or absence of local hidden variables. But KCBS inequality, which was simpler because it's a four-dimensional system, 2 times 2 is 4, KCBS is valid for a three-dimensional single system. It shows a non-locality in time because you do a measurement and then you do either B or E measurement after you did the A measurement. So you change the past if you want, if you try to interpret this as action of one. One last thing about if you bring them together, there is a scenario, there's a competition between the two quantum events. This can never be less than -5, so some people think that there's a monogamy between these contextual behaviors. You either see quantumness in this, or KCBS violation here, or Bell violation between A's and B's. But again, Frat showed that if you use a different scenario, this is not the case. So monogamy, don't take my words to social life, is not a basic thing. Okay, in 5 minutes or so, let us jump to contextuality, from contextuality to quantum computation. When I was very happy with this KCBS paper 10 years ago, 2 of my old students and 2 of my colleagues, unfortunately we lost Shumovsky, there appeared this article in Nature. So, you know, then there should be a connection. Why don't we have then a single qubit which violates or which is contextual, yet no algorithm or quantum computation algorithm? Or the simplest algorithm, in fact. At that time, when you asked this question to Google, it was saying that the answer is Doge. Just to remind you, Doge algorithm that you see in textbooks involves 2 qubits. This is actually older version. You start with 0 and 1 Adamar gates, and if you run your system, you want to decide, by the way, whether your function here is a constant function or balanced function. You can easily simulate your system and look at the final state. If in the final state you see, if you obtain in the upper qubit 0, then it is a constant function. If you obtain 1, you need you have a balanced function. This is classically a question that can be answered classically with 2 calculations, because you should calculate f of 0 and f of 1. But here you solve the problem with 1 calculation, and that is why it is thought to be a simple demonstration of 2-to-1 speed up in quantum computation. But for 3, you can do something similar. Say, when you have a distribution of such 3 balls in 9 boxes, the question is whether your card is in the upper or in the lower row. These are actually 6 permutations of 3. You can easily convince yourself. Classically, you need again 2 calculations, because you should check whether, say, this is full or not. It is full here and it is also full here. You can look at all other examples. But in quantum mechanically, you can solve the problem with 1 calculation. You just write the corresponding unitary transformations. It's a 3-dimensional space in this case, and you have a box. And whether this box is from the first row or from the second row is your question. But if you put M, 1, 2, 3, 4, 1, 2, 3, you don't have any thing different from classical case. But in quantum mechanics, you can do something more. You can, for instance, put your initial state, pass through this so-called Fourier transformer. If you do so, you can easily see that for all evens, the output state is the same. For all odds, output state is the same, and psi 4. Therefore, by the way, unfortunately, I have showed these slides 3 weeks ago in India, And all of a sudden I realized that I said, I tried to say it was chicken, or I should have changed anyway, but they were understanding. At the end of the calculation, you check whether this is 1 or -1, again with single calculation. You might say, by the way, this was first, it is now 5 years ago. Laroche is there. This was just after his Nobel Prize. There was a suggestion by Jörg Rajdrup. He was saying that with NV centers, an experiment can be done. He has never done this. We communicated, but in a year there appeared 4 experiments. I will just mention these first 4 experiments because here today we have more than 10, maybe. Why I did go to India? Because the group by Kavita Dorai was the first group who did the experiment. She had, she is also a lady, Dogra, doing her PhD, and they had this NMR system. They were forming Fourier transformations. They were looking for something, something to do. Then all of a sudden, someone from Turkey wrote an article in arXiv. Before it was published, they did the experiment. And this is a deuterated chloroform. It's a 3-level system. And for odd and even permutations, you obtain in your tomography results indeed the same thing. And let me run the other experiments because time is almost up. I will mention just, you can generalize this to 4-level systems. And you can do the experiments with, by the way, optical systems. Today in the morning, by the way, we had an advertisement for a book. At least here, let me advertise the algorithm. Okay, sorry for that. Next slide. But one thing, the algorithm published after these 4 experiments. That was a sort of a causal situation. Well, how to, one last thing. We also did an experiment, not the NMR experiment, original one, but in IBM computer last year or the year before, it took more citations than the original paper. It was also published in an AIP journal. Well, okay. Now, in -1 minute, there is a refined version of Deutsch algorithm. You can run Deutsch algorithm with single qubit. Deutsch problem, 0,1 to 0,1, is not a unitary transformation. That is why probably Deutsch taught using 2 qubits. But if you use this operation, this is a unitary one. And you can easily see that with this constant and balanced cases, there is a simple distinction because for constant case, if you use plus minus eigenstates of X operator, they remain the same, but for balanced case, they flip. So let's do this calculation. Let's analyze this calculation with mutually unbiased bases. No Hilbert space, no X, Y, Z operators. Prepare your, these are the 3 mutually unbiased bases for dimension 2. Prepare a state in this way. These are the real probabilities. Probabilities and the, you measured in the lab. Well, 1 over 2, 1 over 2, 1 over 2, 1 over 2, and start 1, 0. Run through the box. If it is a Deutsch problem, if it is a balanced one, this 1, 0 becomes 0, 1. But if it is constant, it remains 1, 0. So this is how you can interpret Deutsch's algorithm. The last one, what about the quantum permutation algorithm? These are the 4 bases, mutually unbiased bases for dimension 3. And here, if you look at odd and even permutations for basis 4, you can easily see that the second and third element are switched or not. If it is an even one, they remain the same. Otherwise, they switch or swap. So you this time prepare 1 over 3, 1 over 3, 1 over 3, 1 over 3 all the way, and start with 0, 0, 1. If it remains 0, 0, 1, this is even. If it is odd, it becomes 0, 1, 0. This way of interpretation is not only a forced use of mutually unbiased bases. Mutually unbiased bases, along with other applications, gives us some formulations, some alternative formulations of quantum algorithms. And one other output, Deutsch algorithm and this quantum permutation algorithm, whichever way you call it, are the same. Deutsch algorithm is, in some sense, two-dimensional quantum permutation algorithm. And you can continue in this way in higher dimensions. I think I can stop at this point. Thank you.
We can take some questions.
There is something called Galois fields, fields of finite size. And they also have a size which is prime power.
Yes.
Is it like the funnel planes? I mean,
They are, yes, there are many connections. There are also so-called Latin squares. They are all related. The fields that you mentioned, this is actually how you construct this finite affine plane. Yeah.
I mean, there's a connection between Galois fields and the affine planes. Funnel planes.
As far as I know, yes, yes.
No more questions. Let's thank you for the video.
Okay.